The 26th problem is the mean kinetic energy of nucleon in a nucleus of atomic weight A varies. So your kinetic energy, let's say, is 26th problem. So kinetic energy varies as A to the power of n. And what is the value of n is asked. So in terms of the kinetic energy of a nucleon is a elementary particle, and basically what we have is p square by 2m. So here in this problem, the m is not given, but it is not relevant because what is asked is only value of n. We know that it is proportional to a. So independent of mass, you don't require for solving m for this. So p value, how to get it? So p value you can get, let's say, from the uncertainty principle, delta p delta r will be equal to, let's say, h cross by 2. So your delta p value is h cross divided by 2 times your r, let's say, or delta r value dimension. The radius r value is h cross divided by 2 r naught a to the power of 1 by 2. So let's put this one, your E kinetic energy will be equal to p square divided by 2m. So let's say your p square value, if you want to take this, so let's say the p is going to be here, h cross square divided by, you have a 2m multiply 4 r naught square a to the power of 2 by 3. Is that it? So if you say that proportional to a to the power of minus 2 by 3, and your n value is minus 2. So that will be n. So if it is asked, if the nucleon only given, if it is given neutron, it can be extended. If it is say the neutron, then you can substitute the mass of the neutron, and you should know the R0 value. R0 is 1.5 millimeter. 1.5 millimeter. So when you substitute, you can get in terms of. If it is a proton mass, you can apply. And then once you know the energy, you can multiply this constant to get in terms of MEV business. Okay. Is that clear?
The P that we said.
See, the P and L, basically your, I'm not used to call it, say in the sense you can get it, the value, the change in momentum. It's the value how much you can get it. So, more or less, you will get it. Yeah. Okay. And the next one, I prefer to go with problem number 28. So this 28, let's say you have a reaction when A goes to B plus C, and there will be some Q. Okay. Q is the heat energy that is generated or absorbed. Okay. So depending on the Q value, if it is a positive, it's an exothermic reaction. If it is a negative, endothermic reaction. Okay. So this is one aspect. And in this question, the atomic masses of, let's say, uranium 63, 152, and samarium, let's say 62, 152. Hydrogen or proton H11, and neutron, let's say N01. Or it is given as, let's say, respectively 151 point, let's say 921749, and for samarium is 151.919756, and the proton mass is 1.007825. These are all atomic mass in A and B. So basically, one AMU corresponds to this. I think there is no C here. Once you know this delta M, you simply multiply these, you will get this in terms of MU. One atomic mass unit, and then you will divide. And the mass of the neutron is, so the mass of the neutron will be 1.00, let's say 8665. The value of Q in the following reaction. So let's say you have aluminum plus 1 neutron gives samarium plus proton, and then in this reaction, what could be the Q value? Find the Q value. That is what you ask. So if you want to know the Q, what you should know is the delta mass defect issue. Mass defect is, it's like let's say this is the product and this is the initial. The mass difference between these is what the mass difference. Okay. So mass of this one plus this and subtracting neutron and aluminum mass, you will get delta M. Okay. So you need to find out the delta M value of your Q value. Q value equal to mass of, so let's say, let's call this aluminum plus mass of neutron minus, so let's say mass of so these samarium minus mass multiply 6. So when you get this value in terms of by substituting and then subtracting our value of it. You all have a question to correct or not? Because I do not see any question. Everyone has the question. So take the question paper and read. So quick value mass effect 0.0028 EP. So that will be the atomic mass. So basically the problem is given only the mass effect value Q in terms of A into only instance. That way it is in ED. So dash into 10 to the power of minus 3 AM. So that is what asked in the question paper. And you don't have to multiply C square also, only the mass effect. So that will be 2.8. Okay, so what do you know about the, let's say the liquid drop water? Before going into this, so let's say you have this relation R and then this kind of kinetic energy of the nucleon, second one, and then is the density of the nucleus is depending on the mass number. Is a general question from this topic. No. Why? Why it is not depending on the element? Mass number or element? Is the hydrogen and lead density is same nuclear density. What about the atomic densities? Which one is lighter and which one is heavier? Hydrogen is gas molecule, right? And then lead, gold, these are all what? Heavier. Atomic density. But nuclear density, he says that it is independent. Both will have the same density. How? So let's say again rho is equal to mass divided by volume. Mass of the nucleus is mass of the neutron into atomic mass divided by volume 4 by 3 pi R cube. Your R value is m n a divided by 4. Let's put 3 here. Pi. Your R is R naught a to the power of. So R naught a to the power of 1 by 3 to the whole cube. So if you take that, what will you get? So m n 3 a divided by 4 pi r0 cube into a. So a gets cancelled. So basically it's a 3 times mn divided by 4 r naught. Basically it's a constant. So it is not depending on the element. Nuclear density, whether it is hydrogen or lead, it is independent of the element. Nuclear density is an intrinsic property. And similarly, whether the electron resides inside the nucleus, answer is no. We can very well get from this uncertainty relation. Okay, but still the negative particle coming out from the beta decay happens. The beta decay happens because it is something like whenever there is a change in the neutron into proton. And you all know this, there is inside the nucleus there is a neutron and proton. And the force between them is depending on the charge, type of the charge. Independent of the charge. Nuclear force is a shortest and strongest force and activity is 20 meter, 10 power minus 15 meter. Less than that. And it is nuclear force is same as proton force or proton neutron. Whatever type of the particle inside nucleon, combined we call this a nucleon. So the force is independent of the charge. It is not depending on the charge. Okay. And whenever this converts into neutron, converts into proton, then it releases an electron. Okay. And then in order to associate, there is a anti-neutrino. This came later. Okay. First people were only know about this. So this was beta decay theory and then beta decay expansion. Okay. So what happens if you ask this proton convert into neutron? Then it comes as a positron, Z plus neutrino. Okay. So then you have in the afternoon session we will discuss about whether which kind of reaction is possible with all this stuff. Okay. So this can be also brought here in terms of neutrino. So you just multiply, let's say, they add this neutrino in both sides. So this anti-neutrino gets dissolved, and then only you will get this. Either you can write. So these are all getting some basis. So now let's say the liquid drop model. There are popular models. One is liquid drop model. Why they say it's a liquid drop model? Initial water molecules. The force between the water molecules acting only within that region and looks like a spherical in shape. When you cut in two pieces, again it forms a two spherical, smaller radius. So all those things happen in the nuclear level as well. So that's why this liquid drop model is being considered. And what is the binding energy relation formula? What do you call that? Weizsäcker semi-empirical formula. There is no fundamental origin. Wherever you see empirical, there is no fundamental origin. It's all contribution that they add. So basically, your binding energy is nothing but your EV volume against surface Coulombic plus some kind of asymmetry as E. Okay. Coulombic and asymmetric. Okay. Asymmetry. That depends on let's put this plus or minus. That depending on the nature of the nucleus that you are dealing. So your EV is a volume contribution. Volume is 4 by 3 pi r cube. And again what you will get? 4 by 3 pi r0 square into EV. Okay. And similarly the surface area is pi r square, 4 pi r square. And 4 pi r0 square e to the power of 2 by 3. So 4 pi r square for a sphere, surface area of a sphere. and that initially is subtracted. Right? The Coulombic contribution, your EC is proportional to Z into Z minus 1. That means between the two nuclei, the number of protons and then with the remaining protons. And also it depends on 1 by R. So let's say 1 by R. So when R equal to R naught A to the power of 1 by 2. So therefore this EC is proportional to Z into Z minus 1 and then divided by, let's put this R naught into A to the power of minus 1. So that's how it goes. So depending on the question, maybe what we are going to discuss, the fifth question, the semi-empirical mass formula for the binding energy of nucleus contains a surface fraction term. Basically, these are all fraction terms. You try to correct the exact binding energy value. This term depends on the mass number A of the nucleus S. Very straightforward question. What is asked your ES proportional to, in terms of A, say proportional to A power proportional to the mass number. Let's put this power in. Again, what is N is asked, or N, or how it is varies. So your ES value is again 4 pi R square. Let's say 4 pi R0 square into A to the power of 2 by 2. So therefore your ES proportional to A to the power of 2. So it's a straightforward question. So similarly, it can be asked for with respect to the volume. It can be asked. So what is how the binding energy varies with respect to volume? And if you want to, if they want to twist, they can also say that binding energy per nucleon. So binding energy per in the same problem, it's binding energy per nucleon if they put. That means divided by A. Nucleon is a combination of proton and neutron, and that combination is nothing but atomic mass number A. So binding energy per nucleon in this case proportional to A to the power of 2 by 3 divided by A. So then it's a proportional to A to the power of 2 by 3 minus 1. So then it will become proportional to A to the power of minus 1 by 2. So if you see here the options, A to the power of minus 1 by 3, A to the power of 1 by 3, A to the power of 2 by 3, A. If it is asked binding energy, it is A to the power of 2 by 3. If it is asked binding energy per nucleon, then it is A to the power of minus 1 by 3. So read the question properly. Whatever is asked, then you solve in the rough problem. Then you come back and see which answer is. Okay. So that is the mistake that we have done for several times. Then later, madam identified this. We were doing something wrong. Thanks, guys. Okay. And the correction term, he was asking the correction term. So as the asymmetry term, so you all know that delta can be a positive for even nucleon. So what is the meaning of even nucleon? When I write even nucleon, what do you understand? Even number of protons, even number of neutrons. That's what we call is even. And then negative for R. And then 0 for, so let's say R yield. So what is odd nucleon, odd A nucleon? How do you understand odd number of nucleons? The moment you say odd number, neutron plus proton is odd number. So that means any one of them can be odd or even. It's a mix. One odd and one even, if you add them, you get odd number. Okay. So whereas this one, even, you get even. Odd, sometimes you may get even, sometimes you may get odd. Odd may be added. Okay. So 0 for odd A nucleon. Okay. So even stands for, let's say, proton and neutron. Okay. Now so this is one aspect, and this is the only problem that I have seen for the last 15-year question papers from the liquid doped water. So maybe next year there will be a chance that you may ask one of these. Because so far it was not asked, there is a high chance that it may be asked. You cannot ignore, it's a part of the nucleus. So there may be a high chance that this time we may ask. And so let's say this another model was shell model. So the shell model basically it's like equivalent to atomic vector atom model. In vector atom model, describes various quantum numbers: principal, orbital, then magnetic, orbital, and magnetic spin quantum. These are the four set of quantum numbers. Okay. So if I say any atomic number, let's say for lithium, then what you can write is lithium is at 3. You can say that 1 is 2, 2 is 1. If it is a sodium, Na11, how will you write? 1 is 2, 2 is 2, 2 is 6, and then 3 is 1. So you don't know how to write this. In the same fashion, in the nuclear level also, the nucleons will stack up in a shells. And this model, shell model, predict exactly how the nucleons are organized. Okay. So what are the information that you can get from the shell model? The unpaired nucleon. What is the angular momentum? And once you know the angular momentum, you can directly get the magnetic moment of the system. So nuclear magnetic moment can be estimated. So in this case, this is not here. So anyone knows how this energy levels looks like? Anyone? Forgot? Anyway, there is some kind of 1s here. So s orbit, p, d, f, same orbits are there. But here the energy level gets split up. Okay, depending on j, where j equal to and total angular momentum L plus or minus s, where s is off. The proton and neutron are comes under spin off particles. Okay, they are not fermions because they are fermions. They are off integral spins. So your L is an orbital quantum number. Let's say for S, orbital quantum number is, what is the corresponding L value? 0. So you can say that neighbor orbital quantum number, let's say for S 0, for P 1, B 2, F 3, and so on. The same analogous with respect to the vector atom model. Only difference here is the energy level will be splitting up. Okay. And let's say this is 1s, 1 by 2. So that means how many nucleons can be accommodated here? 1s off. If we say, let's say because you have a L value 0, plus or minus 2 nucleons can be put together. So maximum number of nucleon is 2 here. And then you have 1p energy level. So let's say let's put this 1p. So the moment you have a p, then L value is 1. 1 plus of or 1 minus of. So 1 plus of, it will be split into like this. You have 2 energy levels. So let's say 1p 3 by 2 and then 1p 1 by 2. So why this 1 L plus S comes to the lower than the L minus S if you ask. Okay. The reason is, so if there is a river flowing, is it easy to walk along the river or opposite to the river? Along the river you need to have less energy. If you want to swim, along the river is much easier. Without effort also you can do it. But if you want to swim opposite to the flow, you have to put a lot of energy. So that means L minus S will always have higher energy. Okay? You are negative. That one spin is down to the applied field. So therefore it is opposing. Opposing the field has always higher energy. So this is a higher energy. Then one more, like let's say in this case, your J is 3 by 2. This number represents J. So this notation is, so let's say 2s plus 1 Lj. What do you call this? Is spectral notation. In atomic and molecular physics, also you see the same spectral notation. Now, this is 1 represented here, the principal quantum number 1. First time is Sun. So how many nucleons can be accommodated? 4 here and then 2 here. Okay. So 2, 4 and then 1 more 2. So let's say 2 is, let's say completely filled is 2 number. And then 2, 4, 2, it's again let's say total number is 8. So that means the shell is complete. Like helium, argon, krypton, they are closed shells. So the lithium atom can be written as Li, not lithium, it's lithium can be written as the helium. Okay, helium and then 2s. You can write this. For sodium, it's 11. You can write that neon is a completely filled orbit and then 3s1. Okay, so lithium, sodium, and then rubidium next one. So rubidium or lithium, sodium, potassium. Potassium. Potassium K is basically 19. So you have argon which is 18 and then 4s1. So if you see this 1s, 2s, hydrogen is 1s, 1s, 2s, 3s, 4s, 5s. So that's why this is all the first periodic. They are all s orbits. So same way in nucleon, you have a 1s, 1p. It's completely filled. Okay, this you can say that it's a completely filled. So if you say come up with some kind of oxygen is O, which is 8, and then 16. This is proton number or atomic number, and this is a mass number, 8. So when you have a Z equal to 8 protons are. How the 8 protons are going to occupy? 2 here, 4 here, 2 here. So that's how these orbits are filled. So there is no unpaired element. And how many number of nucleons are there? 16 minus 8 nucleons. So 16 minus 8 is again 8. So that means again 8 neutrons, again the same value will be filled up to this. So that means it's a completely filled orbit. So that is basically it's how the inert gas, helium, neon, argon, krypton. In the same way, nuclear level, whenever you have 7 nuclei, will be completely filled when the orbit is filled. They are called inert, basically. They don't participate in any kind of nuclear reaction levels. Okay, because there is no excess of neutron or proton. So that's what you will get from this. Okay. So let's say you have another energy level. So let's say the next level is let's say 1D. So this 1D will be split into again let's say so 1D. When you have a D, D is 2. 2 plus half is 5 by 2. 1D 3 by 2. So this 1D 3 by 2. And there is one more level, let's say you have a 2s, so that comes into medium. Let's say you have 2s, 1 by 2. Because your 2s energy level is lower than 1d 3 by 2. Like what you see here, let's say 1s2, 2s2, 2p6, 3s2, and then 3p. Sometimes it will come, S will come before because of the low energy. In the same way, your 2s comes before this. The energy velocity. So therefore, what you will have is here, you have another 6 electron, 6 nucleons, 2 nucleon, and then 4 nucleon. So let's say 8, 6 plus 2. Let's say this one is a 28, or let's say, so this is 2 and 8 here, and then up to this, what do you call this? 20. Total 20. So your 1D is filled and 2s is also filled. So that means another complete package. Now if you move on to this, so let's say the next one is 1F, where 1F will be split into these. So let's say 1F 7 by 2 and 1F, because F is 3, 3 plus half is 7 by 2, so 3 minus half is 2 2.5, that is 5 by 2. And in between, there exists, so let's say, you get 2p, and this 2p will come here, and then out. So you put 2p. So we have a 2p 3 by 2, and 2p 1 by 2. So here 4 electrons are there, and here 6 neutrons are there, sorry, and here 8 neutrons are there. So again here 2 neutrons. So if you remember up to this, somehow you can solve a lot of problems from the nuclear physics. Just will emphasize a little bit so that you will understand better. Is it mandatory? Okay, is that clear? Any questions for this one?
So neutron is a love.
See, let's put it as a dividing your proton and neutron. It will be occupied both. For an odd nuclei, one excess, let's say here 1, then it's a vector sum of plus of total value 1 or 0, depending on the ordering. They are parallel or anti-parallel, depends on the vector sum, net result. Otherwise, one side neutron, the other zero. They will have both the energy levels. So what these numbers are called is a magic numbers. Let's say 2, 8, 20, and then 28, and then 28 after is 48, and then 50. So this comes 50. So 2, 8, 20, this is our basic numbers. Basically, this is not required to make 20. So probably I will put here 2 electrons, 6, 4, and then 8. Okay. So the circle ones are called magic numbers. So those numbers, whenever it comes either the proton or a neutron or both, what you will have is a magic number nucleus. And this is the reason the binding energy curve per nucleon, if you plot, what you will have is, so this is what we call nucleon. A, and then binding energy per nucleon, if you draw, initially it is going to be packed up like this kind of sharp tips are there, and then goes and then such. So this is for iron. Iron number is, let's say 26 or 27. Let me see that some number. Let's put this is iron. Iron is the maximum one binding energy per nuclear value. And you will see here the nearest neighbors will drop down. So this will keep on increasing and suddenly there will be dip. And the dip, wherever you look at this binding energy reduction, these are all where the magic number nuclei appears. Because they are completely filled inner. So their binding energy is decreased compared to their nearest neighbors. Okay. Is that clear? So once you know this, what we are going to estimate the J value, total angular momentum, and then the parity of this one. The parity is the concept. So parity is if you move, let's say, from R to minus R, like kind of spatial inversion. So that how this going to change. Okay, it's called the parity is a kind of a sign. Okay, then your values are going to be positive itself or negative itself. Okay, that depends on angular momentum. Let's say parity is defined. It's called this phi. Parity is defined as phi, and this phi equal to minus 1 to the power of n, where n is the orbital angular momentum. So when you say s orbit, the parity is basically the negative, not minus, it's 0. S value is 0. For S, L value is 0. Any number power 0 is 1. It's going to be an even parity. If it is a p orbit, minus, because L equal to 1. It's a negative odd parity. Okay. So wherever this nucleon comes and sitting here, let's say if I put one nucleon here, either proton or neutron, then the spin value is 3 by 2. And the parity is, because it's a p orbit, it's going to be negative, odd parity. So that's all you should understand. When it will come here, after filling this, comes here. So let's say this may be for the lithium. for lithium, and then beryllium. Beryllium you will have 1 up and 1 down will be 4. And then 5 is, fifth one is boron. Boron 5. Again you can be filled in because up to 6 you can come here. Okay. So both the neutron and proton can be filled in parallel. That's why it's a division here. You choose one side proton and the other side neutron. Okay. So, but whichever is completely filled, that is not going to contribute in the any kind of physical quantity. So let's say, for example, is oxygen. Both of them are 8. So that means either proton or neutron will contribute to the physical quantity. The next one, let's say nitrogen. 7 and 16, let's say. Let's put 15. Let's put 14. 7 and 14. Yeah. The proton number is 7. So that means 6 protons completely filled here and then goes here. The next index here. So therefore the spin value is half. Parity will be p orbit or parity. And neutron 14 minus 7. Again 7. One more thing. So then it's a vector sum. Either it can be 1, half plus half, or half minus half. So depending on the situation, that is. If it is another case, let's say if I put it as a 15, your proton still occupies here. What about the neutron? 15 minus 7 is 8. So that this orbit is filled up. So neutron is not going to contribute in the any physical values.
So complete the filter.
Complete the frequency control. Okay. Let's put this 1 up, 1 down for these 2 proton. And then here you have say 1 up, 1 down, and then 1 up, 1 down. So 4 protons are there, and then here. So this is for 7. 2, 4, 6, 6 plus 1, 7. And for 8, let's say 1 up, 1 down, 1 up, 1 down, 1 up, 1 down, 1 up, 1 down. So up to this it's free. So that's how this energy is filled. So initially it's later. Once it is filled, this number, then go to the next. Later, next. And now, so let's say these are the ground state and these are the excited energy. So in the electronic transition, when the excited atom comes to the ground state, it releases what? Photons. Here, it will be gamma. Photon, same photon, but a higher energy. Very high energy. The lambda value is very, very low in terms of the computer. We will see one problem, the energy difference between these two will be given. Or it can be still or still. We will do that problem. Okay. So this is mandatory for sure for the next 1.5 hours at least to solve problems in this session. If you have a question, please ask and clarify. What is the source of this? I am not teaching. I am just explaining how the energy levels in the nuclear level. And this is the theory you might have studied in the MS regular class. And there is a strong theory for this, how this, to explain all this. Any questions so far? Is that clear?
Magic numbers.
Magic numbers are something like you have an 8. So whenever this orbit is completely filled, it's something like helium, neon, argon, where the orbits will be completely filled. So let's say for this one, hydrogen, it's 1, it was not even filled. But whereas helium, 2, yes orbit is completely filled, 2 electrons are filled. When you come to the neon, so neon is 10. So neon is 10 and then 10 electrons are there. 1s2, 2s2, 2p6. So 2 plus 2 plus 4, 4 plus 6. So the electronic configuration is completely filled. If you want to put this, let's say, so let's say this is p orbit. They have 1s orbit, 2s orbit actually. 1s, 2s, 2p6. And what is this one? Subshapes. Px, py, pz. Same thing here also, there is a suborbit. Now L plus orbit, L minus L orbit. So the suborbital levels are called, let's say, you call this as a D axis, different rotation degrees. Okay. So that you will study maybe in the higher levels. Okay. So even this will further split down into orbital level. Okay. So that I am not discussing. Is that clear? So, yes.
Some orbital equations, first order SPE support the subject to work in orbital. Second order 8 orbital.
Second level only 2p3 by 2. There are only 4 electrons, 4 neutrons, 4 nucleons. And then 4 plus 2. There is L plus S, L minus S. That's how they separate the energy level splitting. Okay.
Is suborbital. S orbital
Oh, in S orbital, it's only 2.
P orbital is 8.
Yeah.
V orbital 16.
There is an electronic configuration. You are talking about electronic configuration. In electronic configuration, is something like this. In d orbit, it is maximum 10 electrons. But here, you will have, you see here 6 plus 4. Again, it looks like 10. But what we say is one more energy level that comes in between the 2s. So even if it is filled, then it also completely filled out. It's correct, same analogy. Where only electron is being filled, here both proton and neutron. You have a parallel. Okay. So we have only for spin and parity 1, 2, 3, 4, 5, 6, 7 problems are there, and I list them. Let's say problem number 2, 7, 30, 37, 39, 43, 44. These are the problems only for spin and the parity. So let's say the 7th problem, let's do this. We get back this two later. According to single particle nuclear shell model, the spin parity of the ground state of oxygen 817 is spin and parity is asked. So how many is it? First, for the given information, Z value, number of proton is 8. And then number of neutron value, A minus Z. Never hesitate to write this, A minus Z. Okay. So, let's say, right? And then feed the value 70 minus 8. You will never commit any mistake. Okay. So this one is what? How many number do you know? 9. So that means it's an odd even. Okay, even and odd mixed. So from just now we discussed up to 8 protons, that means it's completely filled up. Now the excess one will go into, so up to this, you can draw one more time the nuclear energy level and then come to this one. So up to 8 it's filled. 9 of the nucleon will go there. Here you consider this side proton. If you want this side proton and then neutron will come here, proton is completely filled. So your this one is 1d, let's say 5 by 2, 1 electron, 1 neutron. 1 neutron is filled in the 1d 5 by 2. Okay, and for d, your parity pi equal to minus 1 to the power of n. Minus 1 to the power of 2, that is a plus. So your spin value is 5 by 2 and the parity is a plus sign. So it's a 5 by 2 plus. So the options are, let's say 1 by 2 minus, 3 by 2 minus, 3 by 2 plus, 5 by 2. So let's understand the parity. So from the viewpoint of parity, you need to know the properties. Your properties is, let's say, j to the power of pi or j to the power of p, where pi or p is known as parity. Your parity value, so let's say your j pi value, let me fix with the pi. Okay. The j pi is 0 plus or even. Nuclei. For all even nuclei, this value, spin and parity value, 0 plus. Because there are only any unpaired proton or neutron. Suppose if this is given as auxiliary 16, then if you fill this one up to 8 and up to 8 is filled, there is no unpaired nucleon available. So therefore spin value is 0. And the parity, you can obviously say that because there is no spin, it's always plus sign, 0 plus. And then in the case of odd nuclei, your parity will become minus 1 to the power. I did my own project again. 6 months. Since then, I still have practice. Okay, so the parity for odd or nuclei. Let's say if it is what we have seen here, the parity, just put L here. Because only one is one, like a neutron we have fixed. Neutron is the one, it's here, odd number. So its L value will be. If both of them are coming here and here, one. One here. Then what you should know is, you should have a different L value. L for proton, LP plus LA. The parity. Imagine a situation where one proton comes here, let's say in this example, proton comes here, and neutron comes in this piece. Now what will happen? Your LP is here, 1. What about the Ln become 2, your D only. So one proton here, one neutron here means your LP is different than Ln. So let's say 8 plus 1, 9. Let's say your number of, let's put this. Another example, let's take is some nuclei which has Z number equal to, let's say 7. And N equal to, let's say 9. Imagine such kind of a nucleus or nucleus. So 7 is, let's say, neutron. Let's say 9 is a 7. So 7 plus 9, if you add, or if it is 16. So Z value is this, N value is 9. Now if you are trying to fill, what you will get? If it is 7, then it is going to be here. Total. And for neutron, 9 means here. So the spin value has a 2 number. So the spin value for proton, it is 1 by 2, and another one is 5 by 2. For neutron, 2 spin values are there. And it is a vector sum. So vector sum means, let's say 1 by 2 minus 5 by 2 modulus to 1 by 2 plus 5 by 2. So all possible values are available. Okay. So what is the difference? Minus 2. So from minus 2 to this one, 3. All values are available. J. Mod is plus 2 and 3. 2 to 3. Either 2 or 3. Okay. So therefore, either 2 or 3, and the parity value, so let's say minus 1 parity pi equal to minus 1 power the For this one, your LP value is 1 plus LP value is 2. So this one LP, angular orbital quantum number for proton, orbital quantum number for neutron. So proton comes here, neutron comes here, and this orbit is a P and this orbit is a D. So for P orbital this L value is 1, for D orbital L value is 2. So 2 plus 1, 3, it's an odd pair. So for all our nuclei is what this. Okay. Okay. Let's move on to the next problem. Spin and parity. Let's go to the so number 2. I won't rename this, but I have pretty easy. So let's say N715 and the spin and parity is, so I hope you can do it. So the options are 1 by 2 minus, 1 by 2 plus, 3 by 2 minus, 3 by 2 plus. It is used on yourself, like the seeds. So basically this seventh question and 39 are the same. But it is asked in 2 different years. If you look at the question paper, the seventh one came in 2011. Then 39 came in and the repeated topic. Once you are familiar with this, then they will not ask for, definitely they will not ask for lead. Okay. Even if it is they are asked, lead is a very unique material, PB 82126. Let's say proton and neutron number, both will have, this is 28, 28, and then 50. The magic numbers are, okay. So the magic number 2, 8, 20, 28, 50, 82, 126. So these are the magic numbers. So basically let's say PB 82 and then 82 plus 126. So that is the mass number. So 6 plus 2, 8, 0, 2, 1. So basically this is the, both of them are magic number. When both proton and neutron comes under the magic nuclei, right? It's called magic number. So it's the highest stability. The material is highest stability. So the moment even if they ask, you don't have to calculate for all this, apply this rule for even nuclei. So your spin is 0, parity is plus. Straightforward, no need to solve. So one of the easiest topic to score. So all these questions you see here, from all of them like to say. Is there any problem with it? Any question? What do we do? Nobody will. Any question? 0 plus. So this is 0 plus. And this one is 1 by 2 minus, and this one also 1 by 2 minus. So the spin and parity is 1 by 2 minus. So what you are supposed to know you should know if the nuclei is coming here. So let's say up to 20, 2, 8 plus 4, 8 plus 6, 14, 15. If anything comes beyond 15, 15 means it should come 2 years 1 by 2. You don't fill directly here. First one, this. So this is where the checkpoint is. So you're supposed to have fill this first and then go to the next. Okay. So we'll have the screen on back here. But any question, please let me know. Filter only the unpaired nucleon is very important. That's what responsible for all kind of properties. Like in the case of in the atomic level, unpaired electron is responsible for the physical quantities. In the same way, the nucleon, whichever is unpaired nucleon, that is what they are responsible. Remaining all intact. Okay. So with respect to the magic number nuclei, we have so the problem number 43, assume that nitrogen 730 undergoes first fermion beta decay from its ground state. Okay, okay, we will discuss this little later because this involves the beta decay process. So after the radiation topic will come back. Okay. Because fermion I need to explain a little bit and then we will start. So far it's clear, right? Yeah. Now let's move on to the magic number nuclei. One more problem is here. Number 46. If nucleons in a nucleus are considered to be confined in a three-dimensional cubical box, then the first four magic numbers are, is the question. So in general, the magic numbers are, so let's say you have a 2, 8, 20, 28. These are first four. Okay. But in the case of when I change this cubical, because it's spherical aspect, now if you move into cubical, how this will appear? Is there any change or not? So let's say your energy, basically what you should know is your energy, your En proportional to, in the case of three-dimensional, the particle in the box case problem. So particle in the box, your En will be equal to N square H cross square divided by 2 pi ml square. Is it? N square pi square is it? Pi square 2 ml square. Okay. If it is in the same problem, it's a one-dimensional box. If it is a three-dimensional box, your En will go into nx square plus ny square plus nz square times, let's say, E1 deeper. Because you did the same. Okay. So basically, it's proportional. So your En proportional to this. Now, the moment you have is okay, so your En is proportional to nx square plus ny square. Let's say nx square, ny square plus nz square. So what will happen is we will start getting the degenerate states. Okay, so the states will increase. You will have if more than one state has the same energy, then you got degenerate state. In this case, only n. For a given n, one energy, one wave function. But here, energy levels will be the same, but you have different states. So therefore, let's say you are nx square, ny square, nz square. let's put this plus here. And then your permutation, and then degeneracy. Let me erase this. And then total. So basically total number of nucleons, basically. Total number of nucleons. That means combination of both either proton or neutron. So let's say the first one is 1 plus 1 plus 1. Is it? So that will be 1 square, 1 square, then 1 square, that is equal to 3. And how many permutations possible? Only one, because nx one, n by 1, nz. So therefore it is only one. And degeneracy is no degeneracy. Only so how many such is a 2 and then 2 nucleon? And then let's say 1 square plus 1 square plus 2 square. So one of them can be in this segment, but still this nx by can be in 1. So why only this? It can also be here. And this can be also here. So 2 square plus 1 square plus 1 square is also same value. So what is this? 1 plus 1, 2, 2 plus 6, 4, 6. And then permutation is 3. 3 different combinations. So the 3 combinations are, let's say, 1 square plus 2 square plus 1 square. So 2 square plus 1 square plus 1 square. So all of them will have 6, and that is what the 3 different possibilities. And now, once we have this number of degeneracy is something like 6 value, because each level can be occupied by 2. So then total number of neutrons will be somewhere around 8. And similarly, if we increase, so let's say we have 1 square plus 1 square plus 3 square. And this will become, let's say, 11. And the degeneracy is going to be 3. Again, same question you can have per group. And then this will become again, let's say, 6. And the number of total will become 20. Again, 1 to 2. But 1 to 2 if you do, so let's say 1 square plus 2 square plus 2 square. So then what will you get?
9.
Or 9. Then it comes here. 1 square plus 2 square plus 2 square. So 4 plus 4, 8, 8 plus 1, 9. So that this should come first. Then it will change. Say, you're right. One square plus 2 square plus 2 square. So 4 plus 1, 9. So this permutation is again 3 will come. So this can be 2, 1, 2, 2, 2, 1. So again 3. And then this will again, let's say, degeneracy is again 6. And then you need to calculate, let's say, 2 plus 6, 8. And then, so 8 plus 6, again 14. The total number is basically first 2, and this is 2 plus 6, 8. And then 2 plus 6 plus this 6. So 8 plus 6 basically 14. And then next one is, let's put this is, if you say that 2 square plus 2 square plus 2 square, this will become what? 12. But whereas 1 square plus 1 square plus 3 square will be 11. So this is the low energy than this. So therefore, it should come before. Okay. So it should come before, and therefore the next energy level is this. And the degeneracy is again 3. And how many possibilities? Again 6. 6 again. So then it is a total. And then you have 2 square plus 2 square plus 2 square, which is 12. And the degeneracy is only 1, and number of electron 2, total is 22. Now the magic number is getting changed. The first 4 are 2, 8, 14, 20. Not like 2, 8, 20, 20. Okay. So how this is changing? That depends on the total energy. So depending on the degeneracy, your numbers also will change. Okay. That's it. Okay. So therefore, from the given options, so let's say you have a 2, 8, 14, 20. So the same kind of problem can even come in the quantum mechanics aspect for filling the electrons. Okay. So somehow they don't want you to get a straightforward question and get the score marks. So they want to filter out. So this is a kind of filtering problem. Okay. So you have to be more careful in such kind of problems. Whenever you see such degeneracies, you have to be more, pay more. Even now I made one small mistake. 1 square plus 1 square plus 3 square. But there is one more like 1, 2, 2. Also possible. Okay. Is that clear? Yeah. Then the next problem I want to discuss is about also. So let's move on to. So to summarize what we have discussed so far is, so let's say we discuss about the radius. So discuss about radius, density, delta M, and then Q value, and J value, parity. These are the properties of a nucleus system. And then now what we discuss about the magic number. Okay. The next one, let's say how the electrons are involved in a diffraction. In the same way, the neutrons also can involve in neutron diffraction. The same laws, same physics. Okay. So for that, this problem number 23 will give you a better understanding. Neutrons move with the speed of 10 to the power of, velocity of the neutron is given, 10 to the power of 3 meter per second. Are used for the determination of crystal structure. So, yeah, big. If the broad angle for the first order diffraction is 30, the interplanar spacing of the crystal is in angstrom. So, given information, mass of the neutron is 1.675 into 10 to the power of minus 27 kilogram. And H value 6.625 10 to the power of minus 34 joules. So it is asked to find the interplanar spacing of the crystal in terms of angstrom. So interplanar and then the general formula is 2d sin theta equal to. So how to get the lambda from the information? De-Broglie wavelength. Okay. So the de-Broglie wavelength can be obtained from, because velocity is given, mass is known, lambda equal to h by p or h by m. So the lambda equal to h divided by m. So your n can be considered as 1. If the problem is not given, n is not given, very well you can consider n equal to 1 as a default. So please do this. I'll get back up to my team. Yeah.